This video is about the shapes of molecules, and the shape of a simple molecule depends on how many pairs of electrons surround the central atom. So a pair of electrons can be a bonding pair or a lone pair, and the pairs of electrons repel because they're negative, so they space around the central atom as much as possible. What I mean by a central atom may be something like carbon in carbon dioxide, where carbon is a central atom and the oxygens are peripheral atoms around the outside. So what I'm going to focus on in each picture is the number of pairs of electrons in each molecule, the drawing of the diagram of the molecule, the bond angle between the bonding pairs of electrons, and the name of the shape. I'm also going to show the dot and cross diagram to show you how I arrive at the diagram of the molecule. So here's the first shape. So it's two bonding pairs, and it's called linear. It's called linear because it's a straight molecule. An example is beryllium chloride, and you can see beryllium has got two electrons, so it can form two pairs of electrons when it bonds to the chlorines. And so that leads to two single bonds, and you can see there are two single bonds here and here. And so the drawing becomes a single bond for this pair and a single bond for that pair. And you can see they're spaced apart as far as possible. 180 degrees is how far they can get away from each other, and that's a linear molecule. The next is three bonding pairs, and it's called trigonal planar, and it has a bond angle of 120 degrees, more on that in a minute. So trigonal meaning three, because there's three bonds, and planar because it's flat. So here's an example, boron trichloride, BCl3. So boron's got 3 electrons in its outer shell, so it can form 1, 2, 3 bonds with 3 different chlorine atoms. So when these bonds, so that means it's going to get 1, 2, 3 bonds here. The way these bonds space out as much as possible is by 120 degrees between them. The next shape is the tetrahedral shape of methane, CH4. Now this is a little bit different, but first each carbon's got 4 electrons in its outer shell, so it can form 1, 2, 3, 4 bonds with 4 different H's. Now what happens here is it becomes a 3D shape. So imagine you've got a ball in the centre, and you're spacing the bonds around the ball as much as possible, so it's not going to be 90 degrees. There's going to be some bonds going forward and back, and so this is what this is showing here. So this is the bond coming forward towards you from the ball. This one's coming away from you to the back of the ball, and there's these 2 bonds here which are neither going forward nor back, they're just going up and then to the side. So how do we show that in chemistry? This means the bond's coming forward towards you, and this means that the bond is coming back away from you. So that's how we draw a 3D shape. Now that's called tetrahedral. If you join these points up here, you'll make a 4-faced polygon. Another four pairs of electrons is where we have 3 bonding pairs and 1 lone pair. So that's called trigonal pyramid. Now what happens here is we've got, so an example is ammonia, NH3. It's got 5 electrons, but it can only form 3 bonding electrons in this case. You see 1, 2 and 3. So that means it's got this electron pair sitting on the top. It's got 1 bond coming forward, 1 bond going back, and then one other bond going neither forward nor back. Now you can see it looks like a pyramid if you join those spaces up, those points up there, and it's called trigonal because it's got a three-point pyramid, so a triangular pyramid essentially. So what about the bond angles? The bond angle between the bonds here is 107 degrees. Now we arrive at that because a lone pair can repel more than a bonding pair. And a lone pair repels the bonding pairs close together because it lies close to the nucleus, and it reduces this bond angle from 109.5, which you would find in methane, to 107. And so it reduces by 2.5 degrees. So that's trigonal pyramid, an example of ammonia. Next one, again it's 4 pairs of electrons, but this time it's 2 bonding pairs and 2 lone pairs. So we got water as the example, which is 104.5 degrees, and we call it V-shape. How do we arrive at that? Well, oxygen's got 6 electrons in its outer shell, so it could form one bond with this H and another bond with that H. So you get 2 lone pairs and 2 bonding pairs. And so this is how you can draw it. And it's drawn in a very similar shape to the tetrahedral. It might be easier to focus on this one here. So this shows tetrahedral, like how it looks a bit like a tetrahedral shape, where you've got the forward H, you've got the backward H, and then you've got the 2 lone pairs, one up, one down. But what happens is these repel each other away from each other, and this pushes these bonding pairs towards each other. So that reduces the bond angle to 104.5. So tetrahedral 109.5 minus 2.5, you get to 107, minus another 2.5, and you get to the V-shaped 104.5 degrees for the bond between the OHs in the water. Now we move to 5 bonding pairs, just 3 left, 5 bonding pairs. So trigonal pyramid is this one here. Trigonal because it's based on triangular based pyramid, and there's 2 pyramids in this. There are 2 bond angles, 120 and 90 degrees. Example is PCl5 or phosphorus pentachloride. So this is a strange molecule because it can form more than 8 electrons in the outer shell for phosphorus. It's called expanding the octet. Uses empty orbitals, and so you can see it's got 5 pairs of electron here. So how does a molecule space out 5 pairs of electrons? Well, you have 1 Cl going up, 1 Cl going down, 1 Cl to the side, and then you've got a Cl going back and a Cl going forward. So we get the 2 bond angles because you get 120 in this planar area, the 3 Cls which I've got coloured in green, and then the angle between the Cl on the top and the Cl, the green Cl, is 90 degrees, or there's 180 degrees between the 2 linear Cls there. So that's called trigonal bipyramid. And then we move on to the 6 bonding pairs, first type. So we have it's called octahedral. An example of that is sulfur hexafluoride. So sulfur hexafluoride is S, it's got 6 electrons, and it can pair up with 6 Fs, so ends up having 12 electrons in its outer shell, which leads to 6 bonding pairs. And this is how we draw 6 bonding pairs for the molecule. So there's 1 up and 1 down, there's 2 coming forward towards us, 2 going away from us. That's how the sulfur spreads out those bonds as effectively as possible to reduce repulsion. It's an octahedral because it's an 8-face polygon. If you join these points up around in here to make a square, and then the points going from that square to the top, that will make 4 faces. Do the same on the bottom, it would make 8 faces. An octahedron is an 8-face polygon. So that, and the bond angle is 90 degrees anywhere you like. It could be there to there, or there, or there to there. It's all 90 degrees between those SF bonds. And finally, 6 pairs of electrons, but this time it's 4 bonding pairs and 2 lone pairs. And this is called square planar. An example is a strange molecule called xenon tetrafluoride. Strange because xenon is a noble gas, so it doesn't react easily. So this is formed in very special conditions. So the xenon ends up having 12 electrons in its outer shell, just like the SF6, the sulfur in SF6. So it forms 1 electron, shares 1 electron with each fluorine. So that means 4 pairs of electrons there. But it's got 4 electrons to spare, so that's 2 lone pairs as well. So we draw the new diagram here, and you can see there's 2 lone pairs are opposite each other because they repel the most. They go opposite each other. And then you've got the 4 fluorines, 2 back and 2 forward. A 90-degree angle between the bonds. We can also show it in this way here as well. And it's called square planar because it's a flat molecule, so these Fs are are all flat to each other. They're in a single plane, and then square because they join up to make a square.